Let's talk about intrinsic semiconductors. What are they? Let's take silicon, for example. Intrinsic silicon semiconductor is actually a silicon crystal that every atom in that crystal is pure silicon. If every atom is pure silicon, we have what we call intrinsic silicon semiconductor. Now, if we look at that, if we look at a crystal, silicon crystal, it might look like this. Remember, silicon has 4 atoms in the valence orbit. So you have an atom here, 4 of them. So that's not enough. The outside atom, the valence atom, must have 8 of them to be stable. So what they're going to do is they share with another silicon. They share actually with 4 of them to be exact. And each one of these, if you imagine there's a stack of them here, I hope the pen doesn't sound bad here. So there's 1 here, there's 2 here, they're sharing these, there's 3, there's 4, there's 5, there's 6, there's 7, there's 8. Every one of these will have 8 of them. So imagine them like all over. Each one of them with 8 electrons. Now, if you remember from before, at ambient temperature, which means at 0 Celsius, these are not moving. At room temperature, they start to move. But silicon is really, it's not a good conductor just because they only have 4 orbits in the outside. So at room temperature is almost this an insulator. So what will happen if I take a negative voltage here and I put a negative voltage to this side of the crystal? This is your crystal right there. And I put a plus voltage right here. Attach this to a voltage source. So I have a voltage source here, plus on this end, minus on that end. And I attach it there. Once the temperature goes above room temperature, every once in a while, electron will get dislodged. So you have this electron sitting right here. And once the electron is actually removed from that spot, that means we have a hole somewhere, so we'll call that a hole here. We have a hole there. Well, the electron is negatively charged, so which means he wants to go away from this end. The electron wants to travel which way? To the left, from negative to positive. The hole, on the other hand, is going to be positively charged. There is no electron in it. So the hole is going to travel from this end to that end. It's going to go to the right. So by adding this voltage here, that thermal energy produces free electrons and holes in pairs. Once the electron is dislodged, we have a hole. So when you have one of these, you have one of these. And they're going to move in that direction. The problem with that is there's not many of them. That's why they call semiconductors. Silicon really doesn't release them easily, doesn't want to give his electron. It's almost an insulator. So how do we make this current going from here to there larger? How do we increase the number of electrons? Well, to do that, we need to do something to that silicon crystal. We need to modify it, add something to it. So one of the options, this option by the way is called doping, adding stuff to it. You can actually add either negative charges, electrons, or you can add holes. So let's talk about doping here, increasing the free electrons. We're going to be adding electrons. Increasing the free electrons. So we're going to add some impurity to that silicon chip. Well, to add impurity to that chip, the first thing we need to do, we need actually to make sure we take this one and melt it, completely melt it. It become a molten. It's a molten silicon. It goes from solid to liquid. Then after it melts, we need to add to it some pentavalent atoms. What's a pentavalent atoms? Pentavalent atoms, these are atoms with 5 electrons in the valence orbits. They have 5 electrons. Not 4, 5. In the valence orbit. So think about this. What kind of element? Look, think of chemistry. What elements have 5 electrons in the valence orbit? Well, that's like arsenic, phosphor, these have 5 electrons in the outer orbit. So when you take an arsenic or a phosphor, here's what's going to happen. There's that arsenic or phosphor there. Now, a silicon is going to come and attach to it. Remember, this has 5 of them. There's a silicon here. There's a silicon here. Each one of these want to make sure they have 8 in them, so they're sharing. This one of them here. And there's 1 here. Wait a minute. This had 5 to start with. So we have an extra electron now floating right here. That's an electron. Free electron. So by adding these atoms, every one of these will actually give you 1 electron. Every phosphor atom will add 1 electron. If you put 50 of them, you have 50 electrons there. And that's increasing the free electron by adding, or increasing the current by adding free electrons to it. The other options, we can do actually holes in them. Just to clarify a few things, this atom actually, because it gives electron, sometimes we call them donor atoms. Because it gives away. It's not looking to take it. It's going to give it away. So each one of these will give you 1 free electron. And so the company who is actually making the crystal for us, the manufacturer, controls the conductivity of doped semiconductors. They can control how many of these atoms to add there. The more impurity that we add to it, the greater the conductivity. So sometimes a semiconductor chip actually may be lightly or heavily doped. A lightly doped one, actually, semiconductor chip has high resistance. It's going to be less current going through it. While a heavily doped chip there, or semiconductor, has a low resistance, which means more current going to go through it. So the more electrons you go through, you add to it, the more current going to go through. It's going to react like a low value of R. The low donors that you put in, that means less current going through it, is going to feel like something is blocking it. That means the resistor must be higher. And that's what's happening. So this process called increasing the free electrons. You might want to do it actually the same thing by adding holes instead of electrons. So let's talk about increasing the free holes there instead of electrons. Increasing the number of holes. In this case, instead of adding pentavalent atoms, we're going to be adding trivalent atoms. So what's a trivalent atom? Trivalent atoms, these are atoms actually with 3 electrons. Atoms with 3 electrons in the valence orbit. Let's think about this. Think again, chemistry. What atoms have 3 electrons in the valence orbit? This could be aluminum, boron, gallium. They all have 3 electrons in the outer orbit. So what will happen if you take an aluminum and you add it to a silicon there? Aluminum has 3 electrons. There's 1 here, there's 1 here, there's 1 here. So what we're going to have is a silicon chip is going to come and share that with it. Now we got an extra 1 here. Another silicon chip will come and share this one with it. That's a silicon. A third one comes in and shares this one. That's a silicon. 1, 2, 3, 4, 5, 6. It's like, uh-oh. What happened? We got sharing this one, sharing this, sharing this. What about if the next one comes in? There's nothing to share. There's only 3 electrons here. So if I have another atom comes in here, we're not really sharing. We have 1 here. That means we have 7 in the outside orbit in the valence. So we have a hole here. In that. So we have a hole in the valence right there in the last orbit of the trivalent atom. So that's why these are called acceptance. Now they're willing, they want to take an electron. If they find any free electron, if there's a free electron floating here, they're going to try to grab the electron to make it 8 atoms in it. So again, that's why these are called acceptors. Acceptors atom or acceptor atoms, you know. I'll go acceptor atoms instead of acceptors. And the reason we call them acceptor, because each one of these holes can accept a free electron during recombination. So now, what happens here? When you mix this material, you can either have a lot of negative charges on the inside, or you can have positive charges on the inside. And that will tell us you can have 2 types of extrinsic semiconductor. What are the 2 types? So we have actually 2 types of extrinsic semiconductors. We'll call the first one the N-type. Semiconductor. I wonder why they call the N-type. Actually, the N stands for negative. That's why it's called the N-type. And what happens here is basically you have a silicon chip like this with more negative charges on the inside than the positive charges. We have a lot more negative, and there's a few plus charges. And if you attach this to a voltage source here, plus minus, the negative charges are called, or in this case electrons, are called what? Major, or the majority carrier there. So the negative charges, or the electrons, are the majority. There's more of them there. Carriers. And the holes, which is the positive charges here, are called the minority carriers. And once you apply the voltage to that, that's your plus minus. So it's going to mark this end negative here. It's going to mark this end positive. Once you apply that voltage, you're actually going to force these electrons inside that, the electrons, to move in this direction. So here's the electron. I'm making that minus charge going to move in this direction. And the hole here is going to go in that direction. So once the hole arrives to this end, an electron from this source will come in and recombine with that hole. Now the other type is called the p-type. Of semiconductor. And you probably guessed it by now, the P stands for what? For positive. That's what the P stands for, positive. And again, since the holes outnumber, so if I have to draw a picture of that, it will look like this. There's only few negative charges here, but the bulk of them are positive. Way more positive than negative. And again, you attach your source to it. So attach the plus side here. And attach the negative here. So we have more positive charges than negative charges. So in this case, what? We call the holes are the majority carriers. And we call the electrons the minority carriers. Again, we can create the n-type by adding atoms that has 5 electrons in the valence orbit, like arsenic, phosphor. That's how we make this one. The positive one, we can create that by melting the silicon crystal, and once it melts, completely melts, then we add to it atoms that has only 3 electrons in the valence orbit, such as what? We talked about aluminum is one of them. Boron, gallium. So you can create the positive one. Now again, the electron here, what will happen? Gonna move from the left to the right. And the hole is gonna go in that direction. The holes, once they arrive at the end of this, just like the other one, an electron will come from the source and recombine with that. So the next question becomes, what will happen if you take a piece that's negatively charged like this, an n-type, and right next to it you attach to it in the same crystal, just touching it, a piece that's positively charged? What's going to happen? And that actually we're going to be looking at that in the next video.